Hello! Today we're going to discuss continuity, which is a natural extension of what we've been talking about in terms of limits. And let's go to the writing mode and I'll explain how. So one of the things that we've noticed is that direct substitution doesn't always work. So direct substitution doesn't always work. Let me remind you what direct substitution is. Direct substitution is when, if you want to take the limit as x approaches a of f of x, direct substitution is when you can just literally plug a into your function. Now this works if f of x is a polynomial, or 2, if f of x is a rational function and f of a is defined. Right? Because remember, the real issue is that what if you plug in a and you get a 0 denominator and that makes it undefined? Recall that this usually happens basically when the quotient rule doesn't work. Okay, so what is like the special ingredient that tells us why direct substitution works sometimes and why it works other times? That is basically continuity. So that's like one reason that continuity is really important. Another reason is that continuity is about the behavior of a function at a point, x equals a. So when we discuss the continuity of a function, you have to talk about the continuity at every single different point. Just like how you could take the limit as x approaches a or some other number, right? You can take the limit at many different points. You can discuss the continuity at many different points. So you can't just say a function is continuous. You have to say, oh, it's continuous at this point, or it is not continuous at this other point. So what is continuity? Continuity, graphically at least, is about there being no breaks or disruptions. Oops, I can't spell. In the graph of f of x. So let me give you an example of when something's not continuous or discontinuous. So let's insert our axes. This is x, this is y, and let's say your function looks like this. Okay, and this is your x equals a. And your function has a closed dot up here. So I would say that f of x is not continuous. So f of x is not continuous at x equals a. Why? Because there's this break in the graph. If you were to follow along with a bunch of points, dot, 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 all of a sudden it jumps up to here and then it keeps going back over here, dot, dot, dot. There's this break. Right? You're going along you're approaching a from the left, you're following that nice continuous line, and then all of a sudden there's this open circle, you have to jump up to that point and then jump back down. That's a break in the graph, it's not continuous there. So we're going to go through, there are 3 things that have to happen for your function to be continuous. So what we're going to discuss is how they go wrong. So there are 3 criteria of continuity. It is easiest to explain them by showing what it looks like when they aren't followed. Okay, so we'll talk about the 3 criteria of continuity. 1. First of all, your function has to be defined at a. Okay, so let's draw an example where this is not true. So let's draw on the x-axis, y-axis. Let's draw our function. Okay, so here's our function f of x. There is an open circle at a. This function is not continuous at a. So in this case, f of x is not continuous at x equals a because the function is not defined there. So basically, for this criteria to hold true, what has to happen? There, you can't have any open circles. Okay. So let me copy this picture because we're going to use it. Okay. So what's the second criteria? Oops. The second criteria is that the limit as x approaches a of f of x must exist. So what would that look like? Well, we've discussed what needs to be true for a limit to not exist. And one of the easiest ways for a limit to not exist is that the limit from the left is not equal to the limit from the right. So what would your function look like? Something like this. We're approaching a from the left, and let's say you go to this point, and then you approach a from the right, and let's say you approach this point. So in this case, you can see that definitely the limit doesn't exist because the two one-sided limits don't agree with each other. Also notice, because I have a filled in dot here, f of a is defined. Okay, so criteria 1 was satisfied, but criteria 2 is not satisfied. The limit does not exist. So you get basically like what looks like two different parts of the graph. There's this jump between them that makes it not continuous. So f of x is not continuous at x equals a because the limit as x approaches a does not exist since the one-sided limits don't agree. Okay, which gets us to our third criteria of continuity. The third criteria of continuity is that, well, the function's going to be defined at a, so f of a will exist. The second criteria tells you that the limit will exist. And the third criteria is that the limit exists, the function's defined, and those two things are actually equal to each other. So this is a good example of how that would go wrong. So notice the limit exists because as you approach a from the left, you're heading towards the open circle, and as you approach a from the right, you're heading towards the open circle. The limit exists. And let's say that that open circle has some y value L. So the limit as x approaches a of f of x equals L. Cool, it exists. The function is also defined because of this red dot right above. let's say that the y value of that red dot is m. So f of a equals m. Unfortunately, these two are not equal to each other. The limit exists and it equals L. The function is defined and it's equal to m. But those two are different. So this function is discontinuous. Oops, it's not letting me type. Let's type it over here. Oops, Fox. F of x is not continuous at x equals a because while the limit exists and the function is defined, in other words, criterion 1 and criteria 2 are satisfied, they are not equal to each other. Now, if you notice, this third criteria is basically direct substitution. So in other words, if your function is continuous, direct substitution is possible. And if direct substitution is not possible, then you are not continuous. That's why I started the video by saying that continuity and direct substitution are really connected in a way. If you think about it in terms of like practically, how do you use continuity in this class a lot? Well, if a function is continuous, it assures you that direct substitution is possible. Or you can think about it the other way around, that if direct substitution is possible, then the function is continuous. Okay. So let's determine the continuity of a function at different points. So basically, how do these examples work? Oh, let's write this. So, oops. So, example, determine the continuity. In other words, figure out if the function is continuous or not of f of x equals x squared minus 4 divided by x minus 2 at x equals 2. And we're also going to justify. Okay, cool. So you basically go in order. 1. Well, to be continuous, you need f of a to be defined. A is the value where you're interested in looking at the continuity. We're told we're looking at 2, so our a equals 2. So you ask yourself, well, is f of 2 defined? So you plug it in. So you're going to get 2 squared minus 4 over 2 minus 2, which is going to be 0 over 0, which is undefined. So right away, we now know that f of x is not continuous at x equals 2 because f of 2 is undefined. Boom. That one's pretty quick. Okay. So you go in order. Criteria 1 did not work, so it's not continuous. If all 3 of the criteria had worked, it would have been continuous. Let's do another example. Determine if the function is continuous at x equals 3. And it's going to be a piecewise function, so I'm going to write it down. It's too hard to type. So f of x is going to be this piecewise function, and it's going to be minus x squared plus 4 when x is less than or equal to 3, 4x minus 8 if x is greater than 3. Okay, so notice we're interested in figuring out the continuity of the function at the point where the graph shifts. Okay, so we go criteria 1. F of a needs to be defined. Okay, we're talking about the continuity at 3, so a is 3. So you ask yourself, is f of 3 defined? Well, it's a piecewise function, and it's for x equals 3, you plug it into that one, so you're going to get minus 3 squared plus 4, which is negative 9 plus 4, which is minus 5. Yes, it is defined. Criteria 1 is satisfied. Okay, let's look at criteria 2. We need the limit as x approaches a of f of x to exist. Okay, which means we need the limit as x approaches 3 of f of x to exist. Now, when does a regular limit exist? When the two one-sided limits exist. And that's important here because it's a piecewise function, right? If you're approaching from the left, you're going to use this function, minus x squared plus 4. But if you're approaching from the right, you're going to use this function, 4x minus 8. So we need to see if those two things are equal to each other. So we're going to do the limit as x approaches 3 from the left of minus x squared plus 4. Well, you notice this is a polynomial, so you can do direct substitution. You plug in 3 and you get minus 5. Yay! Okay, now you need to check the one-sided limit from the right. We'll do the limit as x approaches 3 from the right, and now this will be a 4x minus 8. This is a polynomial, so you can also do direct substitution. You get 4 times 3 minus 8, and what is 12 minus 8? You get 4. And then you're like, oh no. Well, the one-sided limits are not equal to each other, which means the regular limit doesn't exist. So the one-sided limits do not agree with each other, and hence the one-sided limits do not agree with each other, thus the regular limit does not exist. Therefore, the function is not continuous at x equals 3, since the limit does not exist. Boom. Criteria 2 failed. Criteria 1 worked, but criteria 2 failed. The limit did not exist. Okay. Let's do another example. Let's determine if f of x is continuous at x equals 0. Again, we'll do a piecewise function. Piecewise functions usually end up not being continuous for a variety of reasons. So most of our examples of a function not being continuous will involve some sort of piecewise function. Other things too, but yeah. So let's have it be equal to sine x over x. If x is not equal to 0, which is the same thing as saying x is less than 0 or x is greater than 0. And then let's have it be equal to 1 when x is equal to 0. Notice we're talking about the continuity at 0, and that's like where the piecewise function switches between the two things. Okay, so you go through the list. Is f of a defined? Well, you're interested at 0. Is f of 0 defined? Yes, it's equal to 1 by the second line of the piecewise function. When x is 0, it's equal to 1. So criteria 1, good. Okay, now we do criteria 2. Does the limit as x approach a exist? Well, we're looking at the continuity at 0, so you ask yourself, does the limit as x approaches 0 of f of x exist? So that means we need to know if the limit as x approaches 0 of sine x over x exists. Interesting thing, yes it does, and it's equal to 1. That's actually just something called a special limit. This is called a special trig limit. You could actually prove it using the squeeze theorem. I wouldn't expect you to. Just know that whenever you look at the limit of sine x over x as x approaches 0, that's just going to be equal to 1. So it does exist. Criteria 2 is satisfied. Okay, now what's criteria 3? Criteria 3 is that the limit as x approaches a of f of x equals f of a. Well, is that the case? The limit was equal to 1, and what was f of 0 equal to? Also 1. They're equal to each other. All three criteria have been satisfied, so it is continuous. All three criteria are satisfied, so f of x is continuous at x equals 0. Boom. Okay. So I've showed you an example where it is continuous. I've showed you an example where it's not continuous because criteria 2 fails. I showed you an example where it's not continuous because criteria 1 fails. Okay, so if a function is not continuous, we call it discontinuous. So we basically classify into groups the different types of discontinuities. In other words, the different things that occur to make it not continuous. So we're going to talk about that now. The types of discontinuities. Because basically, like you're going to see that certain things happen with the function that make criteria 1, criteria 2, or criteria 3 fail. Okay, and you can actually draw pictures. It is really cool. Okay, so let me quickly set up some axes. And we'll explain this. So here's our xy axis. Okay, we're going to have 3 types of discontinuity, so I just want 3 of these. So it'll be nice and ready for us. There we go. Oh, shoot. Let me move this one a little. Okay, there we go. Okay, so let's say you have a function that looks something like this. So here's our f of x, and we're always interested in the continuity at a point. We usually call that a, so there's your x equals a. We call this a removable discontinuity. So what makes it a removable discontinuity? Well, if you look at this, what you have going on is that the limit as x approaches a of f of x exists, but it's not equal to f of a. So how does that happen? It's because that open circle, let's say it has a value of L, the closed circle has a value of M. As you approach from the left, you're heading towards L. As you approach from the right, you're heading towards L. The limit exists and it's equal to L. But the function is defined and it's equal to M. So you fail the third criteria, basically. A removable discontinuity is when criteria 1, the function is defined, is true. Criteria 2, the limit exists, is true. But criteria 3 fails. Those two aren't equal to each other. Okay. Let's move on to the second type of discontinuity. So in this case, as you approach from the left, you're heading towards L. and as you approach from the right, you're heading towards M. So this is called a jump discontinuity. It's also sometimes called an essential discontinuity. So notice that the limit as x approaches a of f of x does not exist, right? Because the one-sided limits are not the same. So you can think of a jump discontinuity to some extent being where the second criteria fails. Right? The limit doesn't exist. The function is defined. You have that closed circle, but not good enough. The second criteria fails. Okay. Let's move on to the third type of discontinuity. Oh, and I guess I should draw that this is at x equals a right there. So let's do the third discontinuity. Okay, hopefully you can see this. You have basically a vertical asymptote at x equals a. So we call this a infinite discontinuity. It's also sometimes called an essential discontinuity. So an essential discontinuity could either be a jump discontinuity or an infinite discontinuity. Notice that again, criteria 2 fails. The limit as x approaches a. The limit of f of x as x approaches a is equal to infinity, which is basically equivalent to it not existing. Okay? So this sort of gives you a picture. If you look at a graph and you see a vertical asymptote, you're not continuous. If you look at a graph and you see a jump, you're not continuous. If you look at a graph and you see an open hole, you're not continuous. Okay? And what we're going to do now is go through, and I'm going to give you an example of like how you would classify what sort of discontinuity you're dealing with. So example, classify the type of discontinuity at x equals 2. And let's say that our function is going to be x squared minus 4 over x minus 2. Okay. So first of all, we have to show that it is discontinuous. So 1. You notice right away that f of 2 is undefined. Right? You plug in 2, you get 0 on the bottom. So we're definitely not continuous. Now, if you go back up here, how do you tell which type of discontinuity you're dealing with? Well, it depends on whether criteria 3 or criteria 2 doesn't work. If criteria 2, in other words, the limit doesn't exist, is the one that fails, it's going to be a jump or an infinite discontinuity. If it's criteria 3 that fails, the limit exists but it's just not equal to it, it's going to be a removable discontinuity. So let's go and figure out, well, does the limit exist? So let's go and look at the limit as x approaches 2 of x squared minus 4 over x minus 2. So you look at this and you're like, oh, okay, this should remind you of the factor and cancel method and agreeing except at a point. If your f of x is x squared minus 4 over x minus 2, that is x minus 2 times x plus 2 over x minus 2. The x minus 2's cancel, which means now you have a g of x equal to x plus 2. We now know that f of x equals g of x except when x is equal to 2. So they agree except at a point. which means that the limit of f of x is also going to be equal to the limit of g of x. I can now evaluate this by direct substitution. You get 4. So the limit exists. So because the limit exists, we're not dealing with a jump or an infinite discontinuity. Okay, so let's look at 3. Is criteria 3 the thing that doesn't work? We need to see if the limit as x approaches 2 of f of x is equal to f of 2. Well, it's not, because f of 2 is undefined. Oops. So this function is discontinuous since criteria 1 fails. Furthermore, this is a removable discontinuity since the limit exists, but it is not equal to the value of the function, i.e. criteria 3 fails instead of criteria 2. Okay, so how do you know it's a removable discontinuity? Because the limit did exist. If criteria 2 had failed, it would have been a jump or an infinite, but it was criteria 3 that failed, so it's removable. Okay, let's do another one. Example, classify the type of discontinuity at x equals 3. And then we're going to use a piecewise function, so I'm going to draw it. Let's say that f of x equals piecewise function minus x squared plus 4. You might remember this, we dealt with it earlier. If x is less than or equal to 3, and it's going to be 4x minus 8 if x is greater than 3. So again, you go through the criteria. 1. You ask yourself, is f of 3 defined? Yes, it's defined. You plug it into the first line of the piecewise function, you get minus 9 plus 4, you get negative 5, so the function is defined. Okay, then you ask yourself, well, does the limit exist? Well, you have to look at the limit as x approaches 3 of our function. Okay, remember, because it's piecewise, you have to split it up into the two one-sided limits. Alright, so you're going to get the limit as x approaches 3 from the left, which is the same thing as the limit as x approaches 3 of, from the left is going to be minus x squared plus 4. That's a polynomial, you can plug it in, you get minus 5. You have to check to see if the limit as x approaches 3 from the right, so hopefully you remember doing this. Well, that's the same thing as doing the limit as x approaches 3 of 4x minus 8. You get 12 minus 8 is 4. These two are not equal to each other, so the limit does not exist. So the function is discontinuous since criteria 2 fails, i.e. the limit does not exist. This means that we are dealing with either a jump or an infinite discontinuity. We know that it is a jump discontinuity because it would only be infinite if the limit was infinite. So there is a jump discontinuity at x equals 3. Boom. And thank you for watching this video, and that's the end.